In this video, we will be going over section 4.6. Section 4.6 is about areas and average values. We are going to start with this theorem 4.28, sine area and absolute area. Okay, we are going to define what we mean by sine area and what we mean by absolute area. You are kind of familiar with sine area, but we are going to define what is absolute area. Here is what the theorem tells you. For any integrable function f on an interval a comma b, the sine area between the graph of f and the x-axis from x is equal to a to x is equal to b is given by the definite integral a to b f of x dx. Okay, so this is the sine area. Before I go to the second part of the theorem, let's explore this one a little bit. What we mean by the sine area. For that, I'm going to take an example. I'll take my f of x to be x minus 1. My function is, perhaps I could make this f of x. Okay, so f of x is equal to x minus 1. Let's take this example, and here is the interval I'm focusing on, 0 to 3. Okay, I want to talk about the definite integral of f of x from 0 to 3. That is this integral. Okay, of course, you know how to calculate this definite integral. What do you mean by this definite integral? What is the interpretation of that definite integral? That is the signed area. Signed area means the area below the x-axis is counted as a negative area. Area above the x-axis is counted as a positive area, and then you take the sum of those two areas. You take the summation of a negative area and a positive area, and this will be that summation, 3 over 2. Okay, as you can see here, you get a signed area. Okay, you count sum of the areas as negative areas, the areas below the x-axis as negative areas, areas above the x-axis as positive areas. Suppose you actually want to count the areas of these two. You want to count each of the area as a positive area. Then how do you find that area? The area of this piece plus the area of this piece. You want to count both areas as positive areas. Okay, there's a trick for that. The second part answers that question. Okay, second part of the theorem. Let's look at the second part. The absolute area between the graph of f and x-axis from a to b, counting all areas positively, is given by the definite integral a to b absolute value of f of x dx. All what you need to do is, instead of taking f of x, instead of taking the definite integral of f of x, you take the definite integral of absolute value of f of x. Okay, to understand why it gives all the positive areas, why it counts all the areas as positive areas, let's look at the geometry. Let's work on the same example. Suppose I want to count both of these areas as positive areas. What I'm going to do is, instead of integrating this function, I'm going to integrate the absolute value function, absolute value of that function, absolute value of x minus 1. Okay, if I take f of x to be absolute value of x minus 1, you can immediately graph that function using your pre-calculus knowledge. Okay, if you graph that function, you will get a graph like this. All what you need to do is, this piece which is below the x-axis, you have to reflect that about the x-axis and send it to the positive side. It will be like this. Okay, this will be the graph of absolute value of x minus 1. So we have the graph here. As you can see now if you integrate this function, if you take the definite integral of this function from 0 to 3, this function is a positive function. It is greater than or equal to 0. So the definite integral of this function from 0 to 3 will be this area plus this area. Both those areas are automatically positive because the function is positive. But notice that this area is same as this area by symmetry. You just reflect this piece to the other side of the x-axis to get the graph of absolute value of x minus 1, right? Then this is the graph of absolute value of x minus 1. So that means this area is the same as this area. So now if you integrate this function from 0 to 3, you count all the areas as positive areas. Or in other words, you get this area and this area as positive areas, and you get the summation. All right, that's the geometric idea behind this absolute area. Let's move on. Next, we have this definition, the area between two graphs. Okay, if f and g are integrable functions, then the area between the graphs of f and g from x is equal to a to x is equal to b is given by definite integral from a to b absolute value of f of x minus g of x dx. Okay, so if you have two graphs like this is your f of x and this is your g of x. Let's say you want to take the definite integral, you want to find the area between these two graphs in this interval, say a to b. Okay, so the area between those two graphs from a to b would be, you have an area here and you have some area here. Okay, you need to find the summation of these two areas. That's what we mean by the area between two graphs. Okay, the summation of the, first of all, let me say this is your f of x, y is equal to f of x, this is y is equal to g of x. Then the area between these two graphs, these two areas are given by the definite integral from a to b, absolute value of f of x minus g of x. Okay. All right, let's move on. Next, we have another definition, the average value of a function on an interval. Okay, here is how we define the average value of a function on an interval. The average value of an integrable function f on an interval a comma b is defined to be 1 over b minus a times the definite integral of f on a comma b. Okay, or in other words, the average value of f from a to b is defined by this expression, 1 over b minus a times the definite integral of f of x from a to b. Okay, that's how we define the average value. That's purely a definition. Okay, but it's an interesting definition. You will see why it is interesting in the next theorem. The next theorem I want to go over is this theorem, the mean value theorem for integrals. Okay, remember we talked about a mean value theorem in calculus 1. This is the mean value theorem for integrals. Okay, let's see what the theorem tells us. If f is continuous, on a closed interval a comma b, then there exists at least some c in the open interval a comma b such that f of c is equal to 1 over b minus a times the definite integral of f of x from a to b. Would that be true? Would such c exist? Well, if you look at the geometry, you should be able to see that such a c exists. Okay, for this example, I will just take a positive function and explain the scenario, and for any function you can use the same argument. Okay, let's see whether this statement is true. This means nothing but b minus a times f of c is equal to definite integral from a to b f of x dx. This equation is same as this equation. I just multiplied the quantity b minus a to the other side. Okay, so that means we should be able to find some c in this interval, in the open interval a comma b, such that b minus a times f of c is equal to definite integral of f of x from a to b, right? Would that be true? Well, let's look at an example. Suppose you are given a graph like this. This is your f of x. Y is equal to f of x. Okay, so you are on the interval a comma b. Let's say this is your b. First of all, what do you mean by this quantity, a to b f of x dx? We all know that that is the area under the curve in that interval. This area is given by this definite integral. We all know that. Okay, now let's observe a few things here. Okay, first of all, let me mark that area. This is that area. This area is given by this definite integral. Now notice that if I draw a rectangle like this, if I take this rectangle, clearly the area of this rectangle is less than the area under the curve, right? And if I take a rectangle like this, that area is clearly bigger than the area under the curve. What I'm going to do is I'm going to take a horizontal line and I'm going to move that horizontal line between those two vertical bars. We have two vertical bars. The first bar is this one, the other bar is this one. I'm going to move this horizontal line between those two bars. Let me actually mark those two bars here. These are the vertical bars that I'm interested in. I'm starting from here. My horizontal bar is here. I'm moving it upward. When I move it upward, the area of this rectangle is getting bigger, right? And we know that the area of this rectangle is clearly less than the area of the area under the curve. And area of this rectangle is bigger than the area under the curve. Okay? Area of this rectangle is smaller than the area under the curve. Smaller than the area under the curve, and the area of this rectangle is bigger than the area under the curve. That means I should be able to find some height, somewhere in between this height and this height. There should be some height where the rectangle, the area of this rectangle is exactly same as the area under the curve. That should be true because we know that this rectangle, if you take this rectangle, the area of that rectangle is smaller than the area under the curve. Area of this rectangle is bigger than the area under the curve. Then if I move this bar upwards, at some point, I should get a situation where the area of this rectangle is exactly same as the area under the curve, right? It's very logical. So that's the idea. Now, if I can find such a rectangle, what I'm going to do is I'm going to find this x value right here, okay? Okay, let me mark that here. Let's say this is the rectangle that gives the same area as the area under the curve. And then I'm going to find this particular x value. I'm going to call that x value c. If I call that x value c, this value is clearly f of c. Now, as you can see, what is c times, what is a minus b times c? A minus b minus a times f of c. F of c is the height of this rectangle, or you could say width of the rectangle. B minus a is the length of the rectangle. Length times the width, that is the area of the rectangle. So this is exactly b minus a times f of c. Okay, that's the area of the rectangle, and the area of that rectangle should be equal to the area under the curve that is given by this definite integral. Okay, that's the idea. You can always find such a c by moving this bar upward. Okay. All right, that's the geometric idea behind this mean value theorem. Now let's move on. Let's go over an example now. Here is the example that I want to look at first. Consider the region between the graph of a function f and x-axis on -2, 4 as shown here. Here is the picture, by the way. We are asked to express the signed area. The first part, we are asked to express the signed area. Let's work on the first part. How do we find the signed area? Signed area. How can we write an expression for the signed area? Remember, the signed area is given by theorem 4.28. The signed area between the graph of f and the x-axis on the interval from a to b is given by definite integral of f of x from a to b. Okay, so that's so straightforward. So the signed area would be definite integral from -2 to 4. Your interval is -2 to 4 in this case, f of x dx. Of course, the f of x is not explicitly given here. It doesn't matter. We just write f of x. Okay, that's the signed area. And then let's go to the next part. The absolute area of this region in terms of definite integrals of function f that do not involve absolute values. Okay, we know the formula for the absolute area from theorem 4.28. Okay, from theorem 4.28, the absolute area is given by this expression, definite integral of absolute value of f of x dx. Okay, absolute area is equal to minus 2 to 4. You take the definite integral of the absolute value of f of x dx. That's the signed area. By the way, both of these two are from theorem 4.28. Okay. Now, but the question asks us to not to leave absolute value. There cannot be any absolute value. Can we get rid of the absolute value on this interval minus 2 to 4? How can we get rid of the absolute value? Well, what I'm going to do is I'm going to look at the function. If I look at this function, given function, in this interval, my function is negative, right? Then what is the absolute value of that function? How do I find the absolute value of that function when the function is negative? You put another negative sign in front of f, right, to make it positive. So in this region, I'm going to multiply my function by a negative sign. That way we can get rid of the absolute value. Okay, so I'm going to split this definite integral into 3 pieces. One piece is the definite integral on this region. The next piece is definite integral on this piece, and the definite integral on the last piece. I can do that by using the rules that some rule that we learned in previous sections. Okay, so I can write this definite integral as definite integral of f of x from minus 2 to absolute value of f of x from minus 2 to 1. There are 3 intervals here. Minus 2 to 1, 1 to 3, and 3 to 4. Those are the intervals that I'm concerned of. Okay, so first I'm going to take the definite integral from minus 2 to 1. How do I take the definite integral of absolute value of f of x from minus 2 to 1? From minus 2 to 1, my function is negative. So taking the absolute value is same as putting the minus sign in front. So I'm going to write minus f of x in that region dx. Would you agree with me? Remember, my function is negative in that interval. This negative sign will make it positive. That is same as taking the absolute value. Okay, so that's the idea. And then the next piece of integral. Next piece of integral is going to be 1 to 3, definite integral of f of x from 1 to 3. On that interval, my function f of x is positive. If my function f of x is positive, the absolute value of f of x is same as f of x. That is f of x dx. Now I need to take the definite integral on the last interval, that is 3 to 4. How do I handle that? On the interval 3 to 4, again, my function is negative. If my function is negative, to take the absolute value, you have to put an extra minus sign in front. You write minus f of x. This will give you the absolute value. Why is it absolute value? Your f of x is negative. This negative sign will make it positive. Okay, you take the same function value with a positive magnitude. Okay, all right. So now this integral will give you the absolute area. As you can see, this integral does not contain any absolute values. See, there is no absolute value here, no absolute value here, no absolute value here. Okay, you should be able to handle situations like this. All right, that completes that example. Let's move on. Next, let's work on this particular example. Find the area of the region between graphs of f of x is equal to x squared minus x minus 2 and g of x is equal to 4 minus x squared on the interval minus 2, 3. By the way, here are the shapes of those two functions on that interval. This is the function 4 minus x squared, and this is the function x squared minus x minus 2. Okay, so you are asked to find the area between those two graphs. That means this shaded area, this area, this area, and this area. Okay. So basically, we can use this definition 4.29. The area between the graphs are given by the absolute, you integrate the absolute value of the difference from A to B. In fact, your A in this case is -2, B is 3. Okay, so area between the graphs would be definite integral of absolute value of, I'll determine the limits later, absolute value of f of x minus g of x, or you could write g of x minus f of x. It doesn't matter. Let's go with what we have in the theorem. Okay, the theorem we have f of x minus g of x. So let's follow that pattern. That is x squared minus x minus 2 minus 4 minus x squared equals dx. Now the limits of the integration would be -2 to 3. Okay, I moved this a little bit to the left. So this is what you get. Okay, so the absolute area between graphs will be given by the definite integral of this quantity from -2 to 3. Okay, of course, if you simplify this expression, you will get the absolute value of 2x squared minus x minus 6. Okay, so you need to find this definite integral. Okay, definite integral from -2 to 3, the absolute value of 2x squared minus x minus 6. So now, how do you find this definite integral? How would you find this definite integral? Well, to find this definite integral, since this is an absolute value, we need to know the shape of the graph of this function. What I'm going to do is I'm going to graph this one. You know how to graph this one because this is a quadratic function. You know how to graph quadratic functions. Okay, so let me graph that. Before I graph, I'm going to find the zeros of this function. If you take y is equal to 2x squared minus x minus 6, you can find the zeros of this function by setting this to 0. Minus x minus 6 is equal to 0. Then you will get 2x plus 3. The factors of this will be 2x plus 3 times you get 2x plus 3 times x minus 2. That means the zeros would be, your zeros of this polynomial would be x is equal to -3 over 2, x is equal to 2. These are the zeros. Now we can draw a rough sketch of this function, of the graph of the function of this function. Okay, how do you draw a rough sketch? We know that these are the zeros. The x-axis, your graph is going to cross the x-axis at these points. And we know that since the coefficient of x squared is positive, you are going to have a concave up shape. So your graph would look like, this. You have -3 over 2 here, and you have 2 here. It would look like this. Should be a concave up shape because the coefficient of x squared is positive. Okay. So we have the graph of this function. We have graph of y is equal to 2x squared minus x minus 6. All right, now how do we deal with this definite integral? Well, we need to, again, we are going to split this definite integral into few pieces. Okay, how do you handle that? Based on this graph, notice that your function f of x is inside here. Let's say this is your f of x, or let's say this is h of x because we used f of x here. This is your function h of x. Okay, so here in this region, your function is positive. So the absolute value of that function is that function itself. On this region, your function is negative. That means on this region, to find the absolute value, you have to put a minus sign in front of that function. Okay, and on this region, Your absolute value is again going to be the function itself because your function is positive. First of all, notice that the interval that we are concerned would be this interval. This is -2, and the endpoint is right endpoint is 3. That's the interval that we are concerned. Okay, we need to do the definite integral from -2 to 3. So let's split this integral into 3 pieces. Perhaps I'll copy this whole thing to the next page. All right, note that the area between graphs is given by this integral. I'll call the area between graphs A. Okay, for convenience, I will use A. A is equal to this definite integral. That is -2 to 3, absolute value of 2x squared minus x minus 6. Now I'm going to split this integration into 3 parts. So first I'm going to consider the integration on this interval. On this interval, this function is positive because it lies above the x-axis. On this interval, your function is positive. So the absolute value of the function is the function itself. I'm going to take the integration from -2 to -3/2. My function is going to be 2x squared minus x minus 6 itself, dx. And then plus, I'm going to go to the next interval, -3/2 to 2. Now I'm on the interval -3/2 to 2. In that interval, this function 2x squared minus x minus 6 is negative. It lies below the x-axis, that is negative. So the absolute value of that function would be the same thing with a minus sign in front. You put a minus sign in front of this function to make everything positive. That's the way you take the absolute value. For the definition of absolute value, you put a minus sign in front. 2x squared minus x minus 6 dx. The last piece is definite integral from 2 to 3 absolute value of f of x. What is my absolute value of f of x on this interval? On this interval, my function is positive. Your 2x squared minus x minus 6 is positive in that interval. That means the absolute value is the function itself. So you have 2x squared minus x minus 6 dx. Now, if you look at these integrals, there are no absolute values involved here. All you need to do is you need to calculate this definite integral, and this definite integral, and find the final answer. Okay, these are things that we have done. You know the techniques how to find these types of definite integrals from the previous sections. It's a lengthy calculation, yes, but if you do that lengthy calculation, you will get this answer: 466 divided by 24. Please make sure that you check the calculation. Okay. All right, let's move on. Next, I want to go over this particular example. Suppose the function f of x is equal to 0.375x squared describes the height in centimeters of a growing plant x days, after x days. Okay, so the first part asks you to find the average height of the plant during the first 4 days of its growth. Okay, when you say the first 4 days, let's work on part A first before we read part B. When you say first 4 days, that means you are in the interval 0,4. You need to understand that. You are starting at 0. Okay, you count the height after it was planted. Okay, x days after. So you are on the on the interval 0,4 when you talk about first days of its growth. For first 4 days of its growth. Okay, you need to realize that you are on the interval 0,4. All right, so how do you find the average height? Well, by definition, we know that the average height, here is the definition. From definition, we know that the average height is given by, average height of a function f is given by, of course, from A to B. Average height of f from A to B would be 1 over b minus a times the definite integral of f of x from A to B. So the average height is equal to 1 over b minus a. B minus a means 4 minus 0 times the definite integral from 0 to 4. That's your interval, 0 to 4, f of x dx. 0.375 x squared dx. That's the average height. Of course, this is the height. To find the average value of this function, so you integrate to a height function on that interval and you multiply it by 1 over 4 minus 0. Now, if you calculate this definite integral, you will get 2 centimeters. You can, of course, calculate this definite integral using the previous techniques that we did, okay? All right, next part. Let's move on to the next part. Find the average rate of growth of the plant over those 4 days. This time we are asked to find average rate of growth. How do you find the average rate of growth on that interval? The average rate of growth is given by the slope of the secant line on that interval, right? Average rate of growth. Growth is given by the rate of the slope of the secant line. That is f of 4 minus f of 0 divided by 4 minus 0. If you calculate this, you will get 0.375 times 4 squared minus 0.375 times 0 squared divided by 4 minus 0 is, of course, 4. You will get 1.5. It should be a rate, so it should be centimeters per day. Okay, so that's the average rate of growth. That completes that particular example. Let's move on. Here is the last example that I want to go over. Answer the following questions about the function f of x is equal to x squared on the interval 1, 3. Okay. Why does the mean value theorem for integrals apply to this function on this interval? Well, if you want to say why it applies to this particular example, all what you need to do is check the criteria for the mean value theorem. You go to the mean value theorem and see whether this function f satisfies all the criteria. Let's go back to the mean value theorem. Here is the mean value theorem. If f is continuous on a closed interval a comma b, then they are exist. Okay, here is the hypothesis. Let's see whether this hypothesis is satisfied. F should be continuous on a given closed interval a comma b. Let's identify the closed interval given to us, that is 1, 3. Of course, x squared is continuous on this closed interval, so we can apply the mean value theorem. Okay. And then we need to answer this question: what can we conclude from it? The conclusion is that there has to be, by the way, I wrote it down here, since f is continuous on 1, 3, mean value theorem applies. Okay, the conclusion of it is there exists some c between the open interval 1, 3, such that f of c is equal to 1 over b minus a. B minus a is 3 minus 1 times the definite integral from 1 to 3 f of x. F of x is x squared, of course. That's the conclusion. Okay. And then you are asked to interpret this conclusion in terms of an area and in terms of an average value. Okay. First of all, notice that this is nothing but c squared, because I know that my function is f of x is equal to x squared. So f of c is c squared. Okay. Notice that this is the average value. What does this equation tell you? This equation tells you that your average value of your function should be equal to the function height at a point x is equal to c. This is the function height. C squared is the function value at x is equal to c. So that means the average value of your function should be equal to the function height at some point x is equal to c. That's what it tells you in terms of the average value. So let me write it here. Okay, the average value of f on the interval 1, 3 is equal to the height of f at some x is equal to c. Height of f at some x is equal to c means c square. See, the average value is equal to c square. Okay, and then I will leave it for you to justify the other part, the conclusion in terms of area, because I explained a similar thing when I explained the definition of the mean value. All right, let's move on to the next part, last part. Find value c that satisfies the conclusion of the mean value theorem for integrals. Okay, so we need to find this value c. I know that f of c is equal to c squared. All what you need to do is you set c squared is equal to this average value. Of course, this is a known value. You can find this integral. Plug in that here and you multiply that by this to get a number. Okay, so if you do that calculation, you will get, I'll call this equation 1. From equation 1, you get c squared is equal to 13 over 2. Okay, c squared is equal to 13 over 2. So the value of c would be plus or minus square root of 13 over 3. Okay, but notice that here we get two values. From these two values, only the plus answer will be in this interval. Plus square root of 13 over 3 in this interval. The negative answer will not be in this interval. So we discard the negative answer. So the value of c would be, perhaps let me write a statement there. Since c has to be in the interval 1, 3, open interval, the value of c should be plus square root of 13 over 3. Okay, that's the value of c. So we found the right value of c. Notice that this value, the value that we found, is in fact in this interval 1, 3, open interval. Okay. All right. With that, we conclude the section 4.6. I will stop there and I will see you next time.